Ladies and gentlemen, welcome everyone. I'm Dr. Roland A. Drolet, PhD in Biomedical Engineering from the University of Toronto, 1971. I am the developer and inventor of the RUMART PEM system that has helped over 1 million people all over the world who were suffering from all kinds of health problems. Today I'm with my son, François Drolet, gold medalist, Olympic gold medalist in Nagano, Japan, in short track speed skating. So I'm pleased to present this clip to you, and this one is about the rationalized MKS for meter kilogram second system of unit. This is the International Scientific System of Unit, and there is what we call rationalized system and unrationalized, but the difference between the two is just one constant. So what I use and most scientists use is the rationalized MKS system. Okay. So this shortly, I'm not going to go through each to all units, but briefly I just want to mention the basic measuring unit. This is the physical name of the unit, the symbol when we talk about unit, rationalized MKS unit, and here basic rationalized MKS unit. So this, for example, length, when we place an equation just in terms of symbol, length is symbolized by L, mass by M usually, but I added AS for mass because M can be other things as well, okay? And I like AS for atomic spring because I talk a lot about atomic spring. Time, T, charge, Q, the electric charge. Then you have the force, F, work is W as far as I'm concerned. Energy is often used U, but work, energy, it's the same unit really. So we call it joule, but energy, you have different kinds of energy. Joules can be translated to calories, for instance. In heat system, we have 4.18 joule is 1 calorie. 1 calorie being the energy necessary to raise the temperature of 1 cubic centimeter or 1 gram of water at room temperature. To raise it from 1 degree, we call it 1 calorie. It happens to be experimentally 4.18 joule, which is the normal unit. Okay. Then you have power in watt, charge density, rho Q because it's charge density, Q for charge, electric current, I or small r, current density, J in English, electric field, E. Einstein uses often his equation, the most well-known equation in science is E equal mc squared. Yeah. But I don't like the E in this equation because for me, E is the electric field, and so I use W for energy or work. Okay. And Einstein used E because he's mainly talking about mc squared. Okay. In this. Electric potential, we use V for volts. Yeah. Okay. Polarization unit, it's Coulomb per square meter. So Coulomb is the rational MKS unit Coulomb. Okay, these are symbols used for all kinds of units, and this is the name in a rationalized MKS unit. Okay. So L stands for meter in length, mass is kilogram in MKS system. Second, Coulomb for the charge. Newton is the name of the force of Isaac Newton, this English physicist. Okay, and 1 Newton in terms on MKS unit, it's kilogram meter per second square. From his famous equation, mass times acceleration. So that's the definition of the force in units. It's mass times acceleration, okay? So that's called 1 Newton of force, okay? As far as work is concerned, it's joule, but joule is the force multiplied by the distance, okay, in physics. So you have the same unit as the force multiplied by meter unit, so that's kilogram meter square second. Okay, this is interesting because when you have any equation from those you have seen yesterday, you can actually replace the units of each symbol in the equation and see that apple equals apple. Because if you don't use the right units, then you have like apples equal bananas. So that doesn't work to get the right answer, okay?
Yeah.
Now, charge density in MKS system is Coulomb per cubic meter, charge density, okay? And current in MKS system is ampere, okay?
Yeah.
Current density, it's ampere per square meter, it's a density. Electric field, volt per meter, okay? Just remembering here that the electric field across the excitable cell membrane is about 7 million volt per meter, which is only 70 millivolts, but for 100 of 1 millionth of meter. So the electric field in volt per meter is 7 million volts per meter. That's what drives your excitable cell membranes of human.
Really?
Yeah. Okay, so that's why we are so in fire sometimes. Okay, and I just make a parenthesis there. One of the reasons we need to sleep at night is to let the time of the medium surrounding the nervous cell to be re-established, to be able to maintain these discharges across cell membrane. Okay, so some people have done a PhD studying why people need to sleep, and one of them went depressive and he never found the answer. And the answer is this: it's to replenish the medium around the cell, and this doesn't happen instantaneously. It is from the food you ate and that were digested, and it has to come to a state where it can sustain discharges for a whole day. But during the night, it's like we are recharging batteries, and that's an expression used by many people. Okay, I keep on the units, but I like to make some example because this is very important, really, to understand what we're talking about. Polarization, displacement, this is defined here as the electric constant multiplied by the electric field, okay, plus polarization. This is the definition of displacement, electric displacement, okay? E here is electric field. Polarization is in Coulomb per square meter, like number of Coulomb you would have in a parallel plate capacitor. Number of Coulomb is like the quantity of electric charge there, okay? And so if we keep on quickly, the electric resistivity, okay, we call about electric resistance in ohm, but the resistivity is in ohm meter, okay? This is the equation defining resistance, is the integral of the resistivity over a certain distance divided by the surface. That makes the resistance in ohm.
Okay.
This is what was in the equation V equal RI, Ohm's law. Conductivity, this is in the inverse of resistivity. Okay? It's what mho per meter. Okay? And mho is the inverse of ohm. Okay? So this is why resistivity, this is conductivity, is the inverse of resistivity. Okay? So it's one over the other. Okay? Electric resistance, I just talk about it here. Capacitance in farad. So farad is the unit of capacitance. What is capacitance? It's the dielectric constant times the surface of a parallel plate capacitor divided by the distance between the plate. So these are very practical definition. In vacuum, epsilon zero. So the unit of capacitance is farad, and magnetic flux is phi. Okay, it's the summation of the magnetic field over the surface in a magnetic circuit. Magnetic induction, B, is in Weber per square meter, and under the name who first talk about the scientists who first talk about it. But most of the time, people talk about magnetic field as B, but scientifically it's H that is the magnetic field, and B is rather the magnetic induction. Okay. So even scientists use B as magnetic field, but strictly speaking, the magnetic field is H, and it's in ampere turn per meter. Remember the NI formula of magnetics that you said you were going to dream about? Well, that's gets this one. And H here is defined by B, the magnetic induction, divided by magnetic permittivity, okay, of the vacuum, minus M. Here is the magnetization. What is magnetization? It's this term that it's like the capacity of material to build internal magnetic field that goes against the external field that you're trying to impose. So the magnetic field resultant is B over mu 0 minus the magnetization of the material. Okay, so these look a little complicated, but that's all the kinds of things that you need if you want to be coherent when you talk about everything in science. Mm-hmm. Inductance is in Henry, in the name of this guy, and inductance is the little formula I explained earlier. Magnetic permittivity multiplied by the surface of cross-section of the magnetic circuit, n squared number of turns square, and Lm for the length of the magnetic circuit. Okay. At the last page of this, for this clip, we were talking about the MKS system of units quite in detail, but this is the essential physical constant, because there are physical constants, I talk about a few of them, and here these are, I consider are the main one. The symbol here that's used, Avogadro number, you remember, we talked about this, A for angstrom, this means 10 to the minus 10 meter, we call it an angstrom. So we have Planck's constant, its value, 10 to the minus 34 joules second, okay. Boltzmann constant, we showed how it is measured in yesterday's clip. Gas constant, macroscopic gas constant, this is the Avogadro number multiplied by Boltzmann constant, okay? Here I did not place KB because in many texts they don't use the B, but I use a B because I have so many constants in what I'm talking. I have Boltzmann constant, elastic constant, and so I like to use subscript. So this value of the macroscopic gas constant, 8.32. Sometimes it says 8.31. I don't know why it's 32 there, but it's slow. Avogadro number, we've seen it yesterday, 10 to the power 23 multiplied by 6 molecule per gram mole. Velocity of light, we saw it, as Armstrong unit, okay, it's in meter, okay. But this is not a basic unit of the MKS system. It's a derived unit, okay? Because the basic unit of length is meter, kilogram, second, okay? But this is a very small unit. Mu is used for micron unit of length, okay? About the size of one cell, or many cells that are spherical. EV, it's in joule per electron volt. So if you take one electron, you raise its electric potential by 1 volt, we call it 1 electron volt. This is a small energy unit, which is about 1.6 10 to the minus 19 smaller than 1 joule, okay? Electron charge is 1.6 10 to the minus 19, yes, that's right, minus 19 Coulomb, and I've measured it in the Millikan experiment myself when I was in second year of engineering physics, but all the other students couldn't get it, but I did, so I'm very happy about that. I like Millikan for this, because it's a basic unit. Now, the mass of the proton, the mass of the electron, which when you know the charge of the electron, you deviate it in the magnetic field, and the way it is deviated, the radius of the curve gave you the ratio of charge to mass. So you know the charge, you can calculate the mass of the electron. So this is extremely small, 9.11 times 10 to the minus 31 kilogram. We're not talking about milligrams there. We're talking about 10 to the minus 28 milligram. So that's the electron. It's so light, it's crazy. And that is the same electron that gave the name to the internet, email. When you talk about email, it's the electron moving.
Really?
You know, it's this ridiculously small electron, but moving like hell. You know, okay? And in one hydrogen atom, its speed, its velocity around the proton is about 137 the speed of light. And we saw
137 times the speed?
No, 137th.
Okay.
Smaller. 137 smaller than the speed of light. But it's still damn fast, because you go to the moon in 1 second with the speed of light. So then it would take just 137. It would take 2 minutes to the electron to go to the moon. Okay? So epsilon 0, we talk about it. You see farad per meter, but we saw that it could be expressed in many basic units. Mu 0, magnetic permittivity of vacuum, we saw this value. Here I added a new essential constant related to the Raman system, because this is very important to understand what people talk about, because there are many PEMF systems. Companies say all kinds of things, but most of them, they don't know what they're talking about scientifically. It's just marketing talk, you know. But in my case, it's scientific talk. So the inductance of a Maxi 2A, inductance of Raman applicator, okay?
Which is a general applicator.
Which is the Maxi 2A, the large ring applicator, okay? Only one ring. It has the value of 1.07 10 to the minus 3 Henry, or millihenry. Okay, so it's precise. And if we use a formula to calculate the inductance of this coil, Raman coil, Brewer basic electricity book gave a formula to calculate the inductance when there is only one turn of wear,
Okay.
okay, or a loop of wear,
Okay.
and then as a function of the radius of the turn, okay, and the radius of the wear. So suppose you have a big wear, and the electric current flows around the surface of the wear, okay, because of the physics law. So you can calculate with the Breuer's formula, which is this one, you can calculate the inductance if you have only one turn of wear as a function of the size of the wear, okay. Now if you take the formula that I showed you that we use to calculate when there are many turns, in this case you place n equal 1 and length of magnetic circuit like this, you end up that actually you will have L will be equal to mu 0 in magnetic permittivity times radius multiplied by this factor, okay. So, and I have calculated this assuming that for the radius of one ring, maxi-dual ring, is 0.25 meter or 25 centimeter the radius, okay? That's 50 centimeter diameter. Number of turn, 29 turn, okay? So I assume that with the 29 turn, if you consider this like only one turn, it would be about 0.6 centimeter in radius. So just using the formula for one turn, I realized that I get the right answer with this formula. So that's interesting. So I made a relation between this Breuer formula for one turn and the general for n turn. So you won't find this anywhere because I made it real. Okay, Bm is the what we call the Bohr magneton. This is the magnetic moment of the electron going, let's say the electron going around a proton, it creates a magnetic moment perpendicular to this, and that's the value of this magnetic moment. In ampere square meter, it's 9.27, 10 to the minus 24. So it's very small. And the nuclear magneton, which is used in nuclear magnetic resonance system, for instance, for medical imaging, a nuclear magneton is defined as the Bohr magneton divided by 1840, which is the ratio between the mass of the proton and the mass of the electron. Because the mass of the proton is like the sun, and the electron like the planets. The electron is has about 2,000 times less mass than the proton. So that's why one goes around the other. If they would have the equivalent mass, both would be turning against the other, okay? And G is the gravitational constant, which is called from Newton, and its value in the equation, its numerical value is 6.67 10 to the minus 11 in the MKS unit, and this has been measured in laboratory by measuring the force between two beam mass, okay, and making sure that the electrical potential is the same, because just a small electrical charge on it would have a force 10 to the power 32 stronger than the Newton's force. So you have to make damn sure that the voltage is 0. So that's the end of this clip. Thank you for your attention. I hope you enjoyed it. And please keep smiling till the next clip.